Hello, I'm Emrah. I will do an exposure attack on supersingular isogeny diffie-Hellman algorithm. I have two files. I will use two files. Isogeny lib sage. This contains two isogeny functions. I obtained this from somewhere else. It contains isogeny walk and isogeny point. If we give a point P of order L to the E and the curve E, then it returns the isogeny chain phi 0, phi 1 up to phi E minus 1 and the final elliptic curve in the end, phi and the final elliptic curve. The second function, isogeny point, I give the isogeny chain phi and the starting point P, and it returns the final image point of this P under the isogeny phi. Okay, let's go back to isogeny attack. And this is the exposure attack simulation. I wrote this code. Okay, for defining P and E0, we choose LA and LB to be 2 and 3, EA and EB to be 13 and 15. So R prime becomes 2 to the 13 times 3 to the 15 minus 1. It will print parameters, and then also it will print whether P is prime or not. In the second part of this code, I define the FP square, my finite field, where the elliptic curve is defined on, and we also check that this elliptic curve is whether supersingular or not, and the order of this elliptic curve should be P plus 1 square. Okay, let's try. Yes, it gives me the parameters. It says P is true, prime. It gives me the elliptic curve, the starting elliptic curve. It's a supersingular curve, and its order is P plus 1 square. Now we will determine the generators P, Q in the starting curve E0. Before starting this, we will assume that our exposure attack is going to be applied on Alice's first isogeny computation from E0 to EA. That's why I need LA and EA as L and E of L and E. P is PA, Q is QA. But also I need PB and QB coming from the both side. Okay, when I click on this, it gives me a new two pairs of PA, QA and PB, QB. We can try it to change the generators. Okay, and as we see, the order of PA and QA is 8192, which should equal to LA to the EA actually, and it's true. And the order of PB and QB, it should be LB to the EB, and it's true. We put assertions here. Okay, we are good with determining the generators PA, QA, PB, QB. Now, for the starting of our simulation, let's say Alice determines the secret values MR, M. I will use sub R for saying that these are the real values, not to be confused with the later value of M's or R's. These are the real values. Okay, I don't need N actually, just M and R. I start with loading the library, isogeny library, because I will use two functions, isogeny walk and isogeny point here. So in the first step, Alice chooses a secret M between 0 and L to the minus 1, and she computes the kernel point R, M times P plus Q. And by using this kernel point, by the way, M is secret, so R is also secret. By using the kernel point R on E0, the starting curve, we can easily find the phi map from E0 to EA by using the isolation walk function. Also, we compute the images of PB and QB under this map. Phi R is the actual phi map. Okay, let's also print this. For now, for example, M is chosen to be 3 to 8, 3. We can run it again to choose different M's. Okay. Okay, let's stop here. Let's say, okay, once more. Let's say M is chosen to be 8, 3, 8, 5, 7. Okay. So M is secret, R is secret, but EA is a part of Alice's public key. Is public, it's known by the attacker. Now, also as a simulation of the exposed point S. Now, assume that this point S is exposed. This is an intermediate kernel point. To simulate this S, we choose a K between 1 and E minus 1 over 2. Okay, because I want this S to be close to the starting point. The starting elliptic curve. And J is between 0 and E minus 2 minus KR over 2. Okay, because there's a relation between KR and JR. Their sum should be no, there's no relation. I'm sorry. Okay, so K and J, they are the randomly chosen, and S is isogenic point corresponding to the first KR part of the chain, phi chain. Okay, this is the exposed point. I will give the KR and JR, but these are not unknown to the attacker. Attacker only knows S. Let's run it. For 5 and 1, it gives S, this S. We can change this. Okay. Okay, let's stop here. Let's say K is 5, J is 3. Now attacker only knows this number, not even the order. Okay, just knows this. In the first step of the attack, now we can start to apply the steps of the attack. In the first step, the attacker finds K and J, and therefore the isogenic chain from phi 0 to phi k. And of course, the codomain of this phi chain, which is EK. Okay. The attacker starts with E0. In each step, it adds points of order L to the list. And for each point of order L, he constructs the possible phi's and e's, elliptic curves. Okay. You can also remember the picture in the slide. For E0, it starts with different phi's and e's. Then E1, possible phi's and e's. Then choose one of the E2. It goes on like this. Then the attacker search S on the all possibles of e's. If he finds S in one of the elliptic curves, possible elliptic curves, then he stops here, which means he finds K. Also, since he finds K, he can also go backwards and find the chain, phi chain. And using the order of S, because he finds EK, he can easily compute the order of S, right, on this EK. Using the K, he can easily find J. So now attacker has K, J, the elliptic curve EK where S lies on, and the phi, but I'm not going to print the phi because it may be very long, but I will check the length of phi chain. Okay, and also this is just a checking by me, not by the attacker, to check that the phi chain the attacker found, is it same as the real phi chain? Okay. Okay, we run it. Yes, K is 5, J is 3. We found EK. Everything is true. Yeah, okay. Actually, this 5 and 3 is same as 5 and 3 correspond to real values of K and J. So, okay, attacker found K and J as 5 and 3 in the first step. The second step, he's tried to solve S equals to M dash times the phi he found applied to the P plus phi of Q is it whether equal to S or not. I'm sorry, he just solves this equation for M dash. He first computes these two values because he knows phi of K minus 1 to 0, this chain, he knows this chain. So he applies this chain to the starting point, generates P and Q, obtains PK and QK, okay? Then solves the discrete logarithm problem by applying Weyl pairing to S by choosing QK. The Weyl pairing of PK and QK, let's say it's G. The Weyl pairing of S and QK, it's H. Then we solve the discrete logarithm here because H is G to the M dash. So we solve this discrete logarithm here. Okay, and of course we should have the n as a modular as the multiplicative order of G. Now we have M dash. This, yeah, it's 136. So attacker has M dash. And the last step is very easy. It's just a small brute force because we know M dash. The attacker knows M dash. He just tried to find M, and he can easily find because he's just going to solve the congruence, modular congruence, which is M dash is actually congruent to M times L to the J in modulo N. N is the computed here. So M dash and M times L to the J, they are congruent to each other in modulo N. So he tries by starting from MD. In each step he adds N, and this M should be at most L to the E plus J. He tries all of the candidates in this range. If the point S is actually M times PK plus L to the J times QK, then he stops because he found the correct M. But this is actually MJ, this MJ is actually M times L to the J. So we should divide it by L to the J to find the actual secret M. And furthermore, we can check that whether it is a correct M or not by applying this M to starting generators P and Q to find a secret kernel point R. Then we apply, we try to find the isogenies phi and E, and also the images of the points PB and QB under this isogeny. If they are all match to what we are expecting to, this E should be EA. These are the final entry curves, and these are the final image pointers. These are the real ones. These are the corresponding to our guess M. Then we add this M into our list. Okay, let's run it. Yes, so possible secret keys are 3857 or 7953. So let's go back to real video MR. Actually, we can type it here. What's MR? The real video, yes, 3857. So it is in our list. So we successfully applied the exposure attack on this example, SIDH example. Thank you for listening. Goodbye.